Hi everyone, welcome back to ChemHelp ASAP. Today we're talking about kinetics, and specifically we're going to be focusing in on the half-life for both the zero and second order reactions. Let's get started. So I'm going to show you where these equations come from for both our second order and our zero order half-life simultaneously. We're going to assume, again, we have a generic reaction here, A going to B. For our second order reaction, our differential rate law looks like so, with a squared value here. And of course, for our zero order reaction, we have a 0 as the exponent. When we're talking about half-life, we need to get to the integrated rate law. Here is my integrated rate law again for my second order reaction, and here is my integrated rate law for my zero order reaction. When we're talking about half-life, of course, we're talking about a very specific value for T, and it is the time needed for whatever our initial concentration of A is to reach half of that concentration. So we know our ratio of A naught to A, which makes T 1/2 for our second order look like this, and of course T 1/2 for our zero order look like this. You'll notice for both of these, I did specify that these are T 1/2 specifically. So let's work problems both where we're working with a second order reaction and then a zero order reaction. This problem reads, a second order reaction has a half-life of 56.1 seconds. The initial concentration of A is 0.450 molar. We want to calculate K, and then we want to know how much time is required for the reaction to be 35% complete. So you'll notice they did not give us a specific reaction, which is totally fine. We don't need one because we know what our initial concentration is and we have our half-life. We also know that this is a second order reaction, so we know what equation to start with. So again, here is our equation for our half-life of a second order reaction. The first part of the problem asks us to calculate K. Well, we can get K from this expression right here. So let's plug in for the value of our half-life and the value for our initial concentration of A. So here's our expression with our values plugged in. Again, we just put our 56.1 seconds here, and we put in our 0.450 molar here. This makes it very easy to solve for K. So K equals 0.0396, and of course our units here are liters per mole times seconds. So the first part of our problem is complete. We have calculated K. Now for the second part of our problem, we want to know when this is going to be 35% complete. So this is not a full half-life. So that already lets me know that even before I start calculations, I should get an answer that is less than 56.1 seconds. But let's get an actual number of seconds. So let's figure out what our concentration is going to be when the reaction is 35% complete. We know our initial concentration is 0.450 molar here. So to get just our concentration of A at 35% complete, of course, it's whatever our initial concentration is minus this initial concentration times, again, our 35%. And that gives us a concentration of 0.2925 molar. So now that we know what our concentration of A is at 35% complete, we're simply going to use our integrated rate law right here to figure out how much time we need to get to that 35% completeness. I just calculated my concentration of A at 35% complete. I know my value of K because I just calculated it right over here from the half-life. And of course, the problem gives me my initial concentration of A. So at this point, I'm just putting numbers in and I'm going to solve for T. So here is my 1 over 0.2925 times my value for K. Again, I am solving for T and my initial concentration is 0.450 molar. And that gives me a T of 30.2 seconds. So you remember I said, well, if we're 35% complete, we shouldn't quite be at a half-life. And that makes sense. We're not quite at a half-life. Let's also work a problem where we're using the zero order half-life equation. So this problem reads, a reaction is found to be zero order. The value for K for this reaction is 6.14 times 10 to the negative second, and the initial concentration of the reactant is 0.850 molar. So we want to know what is the half-life of this reaction, and then how many half-lives are required for the concentration of the reactant to go to 0.010 molar. Okay, this is a lot of information. Let's just break it down bit by bit. First, we know this is a zero order reaction. That goes ahead and tells us what our equations are that we're going to use. We're also given a value for K, and we're given an initial concentration. Again, we don't have to know exactly what this reaction is. We just know that it's zero order. So the first part of the problem asks us, what is the half-life of this reaction? Well, knowing that it's zero order, here is our equation for half-life for zero order reactions. We need to know our initial concentration, and we need to know our value for K. This is great because the problem gave us our value for K and our initial concentration. So all we need to do is plug these numbers in and calculate our half-life. So plugging in our initial concentration of A, plugging in our value for K, we get a half-life of 6.92 seconds. Okay, fantastic. That is the first part of this problem taken care of. Now we want to know how many half-lives are required for the concentration of the reactant to go down to 0.010 molar. Again, knowing that this reaction is zero order is very powerful because here is my integrated rate law for a zero order reaction. I can calculate how much time is needed for my concentration to be 0.010 molar. So let's plug in what we know. I know what my concentration of A is going to be. That's going to be my 0.010 molar. I have my value for K. The problem gave it to me. I'm trying to calculate T, and I know what my initial concentration is. Again, the problem gave me that as well. Okay, so here are all of my numbers plugged into my calculation. I kind of had to squinch it a little bit because I didn't have a lot of space. So again, here is my concentration of A. Here is my value for K. Don't forget this negative here. That's a very, very common mistake to make. I'm calculating T, and my concentration, my initial concentration of A is 0.85 molar. So simply solving for T, I get a time of 12.2 seconds. So it will take 12.2 seconds for this reaction to get to a concentration of 0.010 molar. But have we answered the question that the problem asked? Well, no, not yet, because we want to know how many half-lives are required to get to this concentration. Right now we know how many seconds are required. And you can see it's not exactly 2 half-lives, it's actually a little bit less. So we're going to need to calculate this. So we're going to take how much time it's required to get to that 0.010 molar concentration divided by the time it takes to go through 1 half-life, and that's going to give us our number of half-lives. Again, it should be a little bit less than 2. When you do this calculation, you find that the number of half-lives is 1.76, which makes sense. We know that it should be a little bit less than 2. It is nice to have those little logic checks. Just make sure that the answers you're getting make sense in the context of the problem. I hope you found this video helpful, and thanks so much for watching.